All right. Welcome back, everyone. How are we doing today?
Pretty good. How are you?
Good, good. It's Wednesday, halfway through the week already. Ish. All right. We're going to take a look at today. If you want to get your notes back out, we're going to be looking at back at pendulums, as we were looking at before. Welcome. All right. So what we're going to get started with is we previously looked at a pendulum, which was just a single mass at the end of a string, which we called a simple pendulum. Today, what we're going to look at is if you have just any sort of object swinging back and forth, that would be a different kind of pendulum that we'll be looking at in here to get started with. So I'm going to put a few things on the board to get started, one of which is when we were talking about previously about simple harmonic motion. I guess I'll just label this here for you. What we're doing today is called a physical pendulum. Okay, and we'll get to that in just a minute, but more specifically what I want us to take a look at is when we look at simple harmonic motion overall, the condition that we had was a sort of differential equation type definition. We said that if you ever had something of the form d squared x dt squared being equal to minus some constant times x, that this is the condition for simple harmonic motion. We recall talking about that before and seeing this equation. We did this, I guess, probably before break, so hopefully we remember this a little bit. This was the condition for simple harmonic motion. If we ever saw this, we knew that an object was going to be moving back and forth following sine and cosine in its different values. And so if we can ever get something to look something like this, whether it's x or any other variable that's in here, if the second derivative of some variable is equal to the equation for the second derivative of some variable with respect to time, is equal to that same equation times a constant, well, a negative constant, then we know whatever that constant is omega squared. And so if we can manipulate the equations to get something that looks kind of like this, we know that it's simple harmonic motion, and we can figure out what the frequency is, or the period is, of the motion based on that constant that's in there. And that's what we're going to be doing today, rather than using just a string with a pendulum bob on the bottom that's swinging back and forth, we're going to be doing this with a physical object that's swinging, rather than something that just has the mass all at the end. The mass is going to be distributed throughout. So we're going to be using rotation to analyze this. Okay, so that's what we're going to start off with here today, is with the physical pendulum. And so a physical pendulum, again, is not a simple pendulum. It's got its mass distributed around. So we'll start off by looking at this like some sort of, blob-like object like this. And let's say that we have it rotating about a point here. Use this. We'll say that we want it to rotate about a point here. Right there. This is going to be our axis of rotation. So it's rotating about that point right there. And what we need to know as well is, well, where's the center of mass of this object? So let's just say that the center of mass is going to be there. Questions about this so far, the setup of this situation. So if we just let go of this object, what's going to happen? Yeah, it's going to swing to the left. Does that make sense? Because at the beginning, At the beginning, the center of mass is off to the side from where it's being supported, and so it's going to swing this way, back towards the center, so that the center of mass is underneath that point. At the beginning as well, if we look at it, well, we can calculate the torque on this object. So what I'm going to do is draw still a couple more vectors on this diagram. So as we've been talking about this before, we measure from the axis of rotation to the point of the center of mass, because at the center of mass, we know that gravity is acting there. It's pulling down, right? So we've got gravity acting on this object right here. That's going to be a force, a downwards force, mg. And that force is acting at a distance away from the axis, a distance d. So what I'm going to do here is draw in a vector. It's going to be this vector there. That is our distance vector from the axis to the point where the force is being applied. So now it's up to you. See if you can figure out the torque on this object. The torque that it feels at this point. Oh, and I guess we should do this as well. I'll drop a vertical line here. We'll call this angle there theta. So if you need to discuss amongst yourselves a little bit, if we remember what torque is in this situation. I've heard it there whispered in the back. We get that the torque is going to be equal to, remember, it was r, the radius vector, crossed with the force vector, so it's the perpendicular component of the radius and the force. So in this case, what that's going to be is mg d, so that's the distance it's applied, so the force times the distance times the sine of the angle between the two. So this is going to be mg d sine theta. Now, the one thing that we need to put in here is that this is actually the torque in this case we're going to say is negative, and the reason why is because if the angular displacement is positive, the torque is in the other direction. So as it rotates this way, the torque pulls it back towards 0 angle. And as it goes this way in the negative direction, then the torque would be positive. So they're in opposite directions. Hopefully that makes sense here in this case. All right. So this is the torque. And just like we've said previously, that's the net torque. That's the total torque on this object. Just like we did with Newton's second law previously. What is our second law of rotation? Can tell us. The net torque is equal to I times alpha. So it's just like we had before, mass times acceleration, but it's rotational mass times rotational acceleration. So this is going to be equal to I alpha. So we're gonna analyze this from a rotation point of view because it's a physical object that's rotating around a point rather than a point mass. So we're not using circular motion like before. We're going to use rotational motion. You can actually analyze the simple pendulum this way as well, and in some ways it's a little easier to analyze it this way. All right, so what we're going to do right now is solve this equation for alpha. So basically all we have to do is divide both sides by the rotational inertia I. And so this is what we get is alpha is equal to minus mg d sine theta over I. And again, this is kind of new for all of us with this one, so just sort of follow along and see what you get. And if you have any questions about it, please let me know as we're going. So this is the equation for the angular acceleration. And if we remember, the angular acceleration is the second time derivative of the angular position of theta. This is equal to d squared theta dt squared. That makes sense? So let's go ahead. Well, we'll do that here in this next step, but this is going to be equal to d squared theta dt squared. And then the other thing that we're going to do is, you remember the small angle approximation? Remember, for this one, we said that sine theta is pretty much equal to theta as long as we're in radians and as long as the angle is small. And so sine theta, we're going to replace with just theta from this step to the next step. Okay? So that's all we're doing on the right-hand side. Is we get then here minus mg d over I times theta. And what you might notice is this is just like the equation that we had at the beginning of class. this is the second derivative of some position variable be equal to negative a constant times that position variable itself. And so here, as theta changes, we're going to get simple harmonic motion, just like we saw with that other one before. And what we know as well is that this constant here is equal to omega squared. mg d over I is equal to omega squared in this case. So that's something that we've just derived. We now have figured out for a physical pendulum that this is the angular frequency, omega, well, the square root of that. And so this is the equation that we just derived for you here. It is mg over I. Now, one thing that's a little different about this compared to a standard pendulum is that this one actually indirectly depends on the mass, because you see the mass in the equation, but the mass does cancel out because the rotational inertia depends on the mass as well. So the actual total mass doesn't come into play here, but the length and the distribution of mass does. And this square root does go all the way down to the, it's not just at the top, it's the whole thing. It's not right. So if you know the rotational inertia and the distance from the point that you are measuring from to the center of mass of the object and the actual mass of the object, and I guess also what gravitation is on the planet that you're on, then you can figure out what the period or the frequency of this pendulum would be. And remember as well that the period is 2 pi over the angular frequency omega. And so we can write this as well, that the period is going to be equal to 2 pi, which is the square root of I over mgd. So these are the equations we're going to be using for a physical pendulum, something that we have, something that we can analyze in this case. How we doing? I remember we're kind of reaching back a little bit here. Okay. So what we're going to do is actually apply this to a few different objects here in class today. The first one we're going to do is a meter stick. So we'll come back to the meter stick here. Let me just erase some of what we got here. Hopefully you have that written down. Do an example. In this case, it is a meter stick. Now, a meter stick about its center is just going to sit there. It's not going to rotate. It's not going to oscillate. So it needs to be a meter stick about somewhere that's not the center. And we're going to just do the end for simplicity right now. So meter stick about its end, we want to figure out what its period is going to be. How long is it going to take for it to swing back and forth? So rather than a pendulum with the mass all at the end, now the mass is distributed throughout. So let's say that this meter stick has a mass of 0.25 kilograms. It doesn't really matter if the mass is going to cancel out in the calculation, but because we're using numbers, some of you guys might find it easier to have a sort of placeholder mass. And what I want you to figure out is, what is the period of this pendulum? So we'll be using the equation we were just deriving there and looking at to come up with the period for this pendulum. You may also need to remember for a rod about its end, you remember what the rotational inertia formula is for that? That's 1/3 ml squared. And so you'll need to use that in your derivation as well. So we'll give you a few minutes to take a look at this one. If you need to talk it out with those around you, feel free. I'll go get a meter stick. Don't worry, that's what I wanted to happen. We're just testing gravity again. We got a period yet? Still working on it? We just said it was going to be equal to 2 pi square root of I over mgd. So I is going to be 1/3 L squared. These masses are going to cancel out, so you don't really need it again, as we were saying. You know what the length is? 1 meter. Yeah. And so as we go through and figure this out, so we can bring the 3 down to the bottom. We can. What do we have for the distance as well? 0.5. Yeah, that's half of a meter because the center of mass, the meter stick, is at its center. So d is 1/2 of the length. So we can go ahead and put that in here as well. This is equal to 1/2 L. And so for any arbitrary, like physical rod that's rotating about its end, this is the equation. I guess we can simplify it a little bit. Let's go ahead and do that here. It's going to be 2 pi square root of 2/3 2L over 3G. All right. And if we plug in 1 for L, what do we get as the period? 16.06? All right. There we get. I think it's 1 point.
I got 1.63.
Yeah, that's what I got as well. I got 1.64 seconds. Here. All right. We good with that? That'll do it. Yep. That'll be a factor of 10 right there. So as we look at this, what I'm going to do is, well, I've got a meter stick. I've got a pivot point here. So does somebody have a timer out for us that they can use? You need to grab a phone out for that. See if we can get this going. So I'm going to put this in here, and hopefully it won't fall off. We'll see. And I'll start it sort of like this. What we'll do is, I don't know, we'll do 5 or 10. That's fine. We'll just do 10. Should take about 14 seconds or 16 seconds there. So we'll wait until it comes back over here for the 10th time, and we'll sort of count it out. So 3, 2, 1, drop. 1, 2, 3, 4, 5, 6, 7, 8, 9, and stop. What do we get?
16.59.
16.59. So I think that's pretty darn good right there. 10 cycles, we get 16.59. So 16.6. That's what, 1.5% off, which I think is pretty darn good, especially because there was a bit more friction in there than we probably would have assumed, which slows it down just a little bit. And so that extended the time just a little bit from what we'd expected. So I think we can say with that the physics indeed works when we look at something in this example. The other thing, too, is since the way that this is set up, I was actually measuring, it's rotating slightly closer to the center than at the very end. So that would also probably induce at least as much as 1 or 2% error from that as well. So what we're going to look at next is one more example of one more object. We're going to look at a solid disk, something like this, but being rotated rather than about its center or about its end. We're going to rotate about a point halfway between its center and the outer radius. And we've already done that before, looking at, like, figuring out the rotational inertia, that sort of thing. What we're going to do here is figure out what's the period that will oscillate back and forth at with respect to time. So I'll set it up on the board, but you can get started with that one if you know what you're doing with that one already.
What's the radius?
R.
This is a mass M.
Yeah, it has a mass of M and a radius of R, and we're rotating about, if this is the center of mass here, we're rotating about this point right there. I guess I'll use the same color I was using earlier. Use the pink for the axis of rotation. And we want to know what is the period. Yep, so the rotational inertia about the center of mass of a disk is 1/2 mr squared. This is one that unfortunately I don't have a physical example of, so we can't test this one after we figure it out. But we've already tested one thing today. I think that it should work if we did it again. Yeah, you won't get a number for the answer here because I didn't give you a value for the radius. But your formula at the end should depend only on the radius and g. And constants. So what we need to look at, again, in this case, is, well, we're just going to plug it into the equation we've got so far for this, which was 2 pi square root of I over md. Now, this is an equation that you won't see on the equation sheet. This isn't on there, I don't think, for the physical pendulum. So if you needed this one, you'd need to go through and derive it the way that we did in class, if you ever needed something like this. I don't know if I've seen this on... No, I have seen this on the AP test. I think it was on the one 2 years ago. So looking through this, hopefully you've been writing down as we've been going through it. I do have these notes available as well if you need them. But for this one, we're going to go ahead and use this equation right here. So do we just plug in 1/2 mr squared over mgd? Nope. No. It's not going to work because this is the rotational inertia about the center of mass. So how do we figure out the rotational inertia about here?
Parallel axis theorem.
We're going to ask Pat. Parallel axis theorem. So Pat says that the rotational inertia about any point, the new rotational inertia is going to be equal to the one about the center of mass plus its new mass times the distance. Or, I don't know why I said new mass, it's the same mass. The mass times the distance from the center mass to the new axis that we're looking at. And so in this case, that's going to be, is it just 3/4 mr squared?
Yeah. That's what I got.
Yeah, so what we're going to do there, it's going to be 1/2 mr squared plus m times r over 2 squared, which is another 1/4 in there. And so we wind up with the new value value is going to be 3/4 m r squared. And so that's what goes in here. And so we get 2 pi square root of 3/4 mr squared divided by mg. And what is our value for the distance in this case? The distance from our rotation point to the center of mass is r/2. And so then if we simplify, we wind up with this being equal to 2 pi square root of, this then becomes 4/3, and that becomes a 2 on the top. Wait, 2 on the top, is that right? No, these cancel, right? Yeah, 3/4, there we go, that's it. So it's 3/2. No, the m's cancel as well. Let's fix that. Go cancel the m's. We wind up with r on the top, g on the bottom. So it looks pretty similar to what we had before, but in this case, there's a constant associated with it. Now, one thing that we might be curious about is, like, how does this compare to if we just had a mass, a distance of r/2 away, like a simple pendulum? So if we just treated it like it was a point mass on the end of a rope, how much different is it going to be in that case? Well, what we would get in that case would have been, if it was a point mass, we would have then just gotten 2 pi square root of L/g. And L in this case would have been r/2, which is kind of a weird way to do it, but just to compare the two, what we would have gotten then is that the period would be equal to 2 pi times the square root of r/2g. Yeah. And so you can see the difference there is a factor of square root of 3. The period is √3 times longer, which is about almost twice as long. You know, it's what, 80% longer, something like that, 85% longer. And so that's what we wind up with in this case, is about 80% longer period than we would have if it was just a single point mass that was the same mass, only at this distance away. So by putting that additional mass farther away from the rotation point, it makes it take longer to rotate, which I think makes sense intuitively in that case. Now, let's think about this example. Back to the meter stick. We had, for that one, what was the, we had, it was, well, we got 1.64 seconds would be the period for this. And if you guys remember, I think that we got for a meter long pendulum, it was 2 seconds to go through one, just about 2 seconds to go through one full oscillation. If you guys remember, we did that calculation earlier on in here. And so, because in this case, we've taken what was a mass that was all at the end and distributed along the length. Some of the mass is now closer than it was before. It lowers the rotational inertia. And so it's easier for it to rotate than it was before. However, the thing about it is that now the center mass is here in the center rather than at the end, whereas when it was at the end, that would give it a larger torque. So there's this sort of double factor in there that makes it take less time with this one than with the other one. So it's one of those things that's kind of interesting in looking at what the difference is between actually taking all the pieces into consideration versus just looking at the simplified pendulum with the single mass at the end of the string. And so that's what this approach takes. As we looking at this, we can figure out as a function of time, we can figure out all that stuff. So let's do that real quick. If we can write down the equation, let's say that it starts off with some displacement at the beginning. I guess I kind of need to draw this out. Let's see if I can do this correctly. So if it's sort of displaced by some angle here, we'll call this theta naught. Okay, so theta naught is our original theta. That's going to be theta at time t equals 0. And let's see if we can write out the equation for theta as a function of time. Maybe omega as a function of time, alpha as a function of time. Because for this object here, using the period that we've got there, or, well, really, you might want to use omega instead of the period for that. Let's see if we can do it. We can write out that equation for this one. As we recall, we typically use cosine theta, as we can write this out as well. What did we get in here? It was 2/3 or was it 3/2?
For I? Oh, yeah.
So that's our value for omega. Going to be equal to, remember we had it was basically just the amplitude times cosine omega t plus phi. But in this case, phi would just be 0. So this is going to be equal to theta naught, the initial angle, times cosine of omega t. And omega is this number there. And then we can just take the derivative of that twice to figure out what omega as a function of time is and what alpha as a function of time is. Now, there is one thing to point out here that's is a somewhat important thing. Sometimes this is called omega naught, and partially that's just to differentiate it from the fact that this omega is the angular frequency, whereas if I take the derivative of this, then I'm still using the symbol omega, but this is omega as a function of time. That's the angular speed, the angular velocity as a function of time. It can get confusing. This is like one of the only times during the year that we wind up having like the same symbol in the same problem, meaning two different things. So that's just a thing to watch out for, is that these omegas are not the same as you see them there. So we take the derivative of this, we wind up with then minus this omega times this theta naught times square root of 2g over r times sine of the same thing and a thing to notice is that this value here, what does that value give us?
The period.
Not period? Almost. Amplitude of what?
Wait, doesn't that give us velocity? Omega squared?
It gives us the maximum
Velocity.
angular velocity. Because keep in mind, the biggest value sine can be is 1. So this number here would be the maximum angular velocity. And so if we wanted to figure out like how fast was the bottom point of this moving as it was swinging through the bottom, well, we could use that to figure out what the maximum value of omega is, multiplied by the distance, which is 3/4 or 3/2 times the radius. That's how far this bottom point is away from the axis of rotation. And we could use that to figure out how fast the bottom point of the thing is swinging as it swings through the bottom. Or you could use energy if you'd prefer to do it that way. But this is an alternate way to do a similar question in that regard. And then if we did this one more time, we would get alpha as a function of time, which is going to be equal to minus theta times omega naught squared, which is just going to be 2g over 3r, times then it's going to be again cosine of the same thing. And as we had expected, we took this derivative twice. We got the same thing we had at the beginning, but times a negative constant. It's the same exact equation, but just times negative 2g over 3r, which is omega squared in this case. So we take the second derivative, and this then satisfies that condition we talked about at the very beginning of class. Whew. So, that was a lot. But that's basically all of pendulums, all of oscillation for the most part. We did it in, 3 days. So
Nice.
let's grab out the WebAssign. We've got a few minutes here to take a look at the homework.
Tomorrow.
No, test's going to be like next Wednesday.
Oh.
Although, but there's still another unit to do before then. We got gravitation.
Oh.
Yeah. So we got one more unit before the end of the semester.
This is brutal.
Wait, when are we gonna study for finals?
We've been studying for finals the whole year
Fair.
in here because we keep doing everything.
Everything is
It's not
all
like
together.
any of the other stuff we've done before. We've stopped using
Oh,
it.
we forgot how to do
We're still
kinematics.
using kinematics. We're
Oh,
still
wait,
using.
Yes.
What do you mean? You guys know how to do all of kinematics. Kinematics is just calculus, and you've been learning calculus all year.
True. And too bad.
There you go.
That's the.
Except for those of you who decided to take calculus before
Yes.
Yeah,
and aren't taking any more of it this year. Because then yeah, you
that might be tough.